In this week's lab, we're going to be working with ice core data to see what we can learn about how and why climate changes from measurements made on ice cores. Now, there's a lot of different kind of measurements you can make on ice cores. The two best known are measurements of the ratios of hydrogen and oxygen isotopes in the ice itself. Ratios of those isotopes change as a function of changes in temperature. We'll talk about why in a minute. The other really well-known measurement that can be made on ice cores is much more straightforward. As snow compacts into glacier ice, small bubbles are trapped in that ice that preserve samples of the atmosphere that date to the time that snow accumulated into glacier ice. We can melt those bubbles down in a vacuum, extract the gases, measure the concentrations of atmospheric gases that we might be interested in, like the greenhouse gases carbon dioxide and methane, to see how the concentration of CO2 and methane in the atmosphere have changed over time due to a variety of different processes. Photos on this slide show you what an ice core looks like. Ice cores are drilled from glaciers and ice sheets, have to be kept frozen, obviously, until we can make those measurements. On the right here, we see a small sample of ice cut from an ice core. You can see trapped within that ice are numerous bubbles of various sizes. It's on those bubbles that we're going to measure the concentrations of greenhouse gases. We're going to melt that ice in a vacuum chamber, extract the gases from those bubbles by doing so, and measure the concentrations of CO2 and methane. At the same time, ice is, of course, H2O, so it contains both hydrogen and oxygen isotopes. Ratios of different hydrogen or oxygen isotopes are a reflection of temperature changes. So you can see why being able to make measurements or obtain data on past changes in temperature and atmospheric greenhouse gas concentrations might be useful if we want to understand how current changes in temperature and greenhouse gases compare to those in the past, and where we might be going in the future with respect to climate as the amount of greenhouse gases in the atmosphere increases due to fossil fuel use. So to obtain information on past temperature changes from ice cores, we're going to be measuring ratios of hydrogen or oxygen isotopes. In other words, we're going to be measuring the ratios of hydrogen and oxygen atoms with different masses. Again, isotope, atoms of the same element, but have different masses because they have different numbers of neutrons. Turns out that there's two common stable isotopes of oxygen, oxygen 16, 8 protons, 8 neutrons, and oxygen 18, which is a little bit heavier, because although it has 8 protons, that's how many you need to have oxygen, it actually has 2 more neutrons, 10 neutrons in total, giving it a higher atomic mass. Water molecules also contain hydrogen, and there are 2 stable isotopes of hydrogen. Normal hydrogen, the light hydrogen, is just a proton, no neutron, atomic mass of 1. Heavy hydrogen has a proton and a neutron, atomic mass of 2. It's twice as heavy as normal hydrogen. That type of hydrogen is called deuterium, or D for short. There's a third isotope of hydrogen called tritium, but that isotope is not stable. It's radioactive, meaning it has too much mass in its nucleus. It's going to spontaneously decay, kick mass out of the nucleus to obtain a lighter atomic configuration. So again, you can have stable isotopes, you can have radioactive isotopes. In ice cores, we're measuring predominantly stable isotopes. Ratio of oxygen 18 and oxygen 16, or the ratio of light hydrogen and heavy hydrogen, also called deuterium. Now, when making isotope measurements, we're also always measuring the ratio of heavy to light isotope. For example, O18 to O16, or heavy hydrogen deuterium to normal hydrogen H. And we're reporting those measurements relative to some reference material or standard. The standard for water isotopes, oxygen hydrogen isotopes, are their ratios in today's ocean. So again, ratio of heavy to light isotope in the sample minus ratio of heavy to light isotope in the standard divided by the ratio of heavy to light isotope in the standard. In this example, we're measuring delta O18, the ratio of heavy oxygen 18 to light oxygen 16 in our sample relative to a standard. We can measure hydrogen isotopes in the same way. Delta D, the heavy isotope, would simply be the ratio of heavy to light hydrogen in the sample minus the ratio of heavy to light hydrogen in the standard divided by the ratio of heavy to light hydrogen in the standard. In other words, isotope measurements are reported as ratios of heavy to light in a sample relative to a standard. For hydrogen-oxygen isotopes, the standard is the modern isotope ratio in seawater. What is the current abundance of these isotopes in today's ocean? Now, isotopes have differences in mass. As a result, they undergo a process called fractionation whenever they undergo a phase change. What is a phase change? Well, a phase change is something like change from solid to liquid, or change from liquid to gas. Well, with respect to water molecules, of course, water evaporates from the ocean. It's going from liquid to vapor. That's an example of a phase change. And then water vapor condenses in the atmosphere to form precipitation, going from vapor back to liquid. And so that is also an example of a phase change. Because water molecules with different isotopes have different masses, they undergo fractionation during those phase changes. Water molecules containing the lighter O16 isotope have a lower mass. As a result, they're easier to evaporate. In other words, the water vapor has a higher abundance of O16. There's more O16 in the vapor compared to the liquid from which it came. The opposite is true for heavy water molecules that contain, say, the deuterium or the oxygen 18 isotope. They have a larger mass. As a result, there's less of those heavy water molecules in the vapor compared to the liquid. In other words, due to differences in mass, light isotopes tend to evaporate, heavy isotopes tend to remain in the ocean. And so as a result of fractionation, our water vapor that we make is lighter. It's enriched in the light isotopes, normal hydrogen and the light O16 isotope. That gives it a negative delta value. In other words, the ratio of heavy to light isotope is smaller in the vapor because this is a larger number. More of the light isotope is getting into the vapor. Fewer molecules containing the heavy isotope are getting into the vapor, giving the vapor a negative delta value. The remaining ocean, in contrast, gets heavier. By that, I mean it becomes enriched or concentrated in water molecules containing the heavy isotopes, such as oxygen 18 or deuterium. In other words, the ratio of heavy to light isotope gets larger, whether we're talking about hydrogen isotopes or oxygen isotopes, and that gives the liquid a delta positive value. But where does the temperature information come in? The light isotope's always easier to evaporate. The heavier isotope tends to remain in the water. But the amount of fractionation, in other words, how strongly the isotopes fractionate by mass, depends on the temperature. When it's warmer, the fractionation effect is weaker. Meaning at warmer temperatures, more of the heavy isotope is able to get into the vapor. It's a little bit easier to get the heavy isotope to evaporate at warmer temperatures. As a result, the ratio of heavy to light isotope gets larger, and the delta value becomes less negative. The opposite is true of colder temperatures. The fractionation effect is stronger at colder temperatures. It becomes much more difficult to get the heavy isotope to evaporate at colder temperatures. Even less of it gets into the vapor. The vapor, in contrast, becomes enriched, strongly enriched, in light isotopes, meaning the ratio of heavy to light isotopes gets smaller, and the delta becomes more negative as a result. So to sum up, the extent of fractionation depends on temperature. Heavy isotopes are always harder to evaporate. How hard they are to evaporate depends on the temperature. At warmer temperatures, it's not so hard. More of the heavy isotope gets into the vapor. As a result, the vapor has a larger heavy to light isotope ratio and a less negative delta value. It's still negative because it's harder for the heavy isotope to evaporate. It's just a question of how much. At warmer temperatures, it's not quite as hard. A little bit more of it is able to get into the vapor, and our delta values become less negative as a result. Conversely, at colder temperatures, the fractionation effect is stronger. It gets much harder to get the heavy isotope to evaporate and into the vapor. The ratio of heavy to light isotopes gets smaller as a result, and our delta values become more strongly negative. So when snow accumulates year after year to make glacier ice, it's recording changes in the isotope ratio as a function of the temperature at which that snow was made. At colder temperatures, the snow contains fewer heavy isotopes. The ratio of heavy to light isotope gets smaller, and our delta value becomes more negative at colder temperatures. The reverse is true at warmer temperatures. More heavy isotopes getting into the vapor, and hence getting into the snow made from that vapor. Ratio of heavy to light isotope gets larger, and our delta value becomes less negative as a result. Measurements of the changes in the hydrogen or oxygen isotope ratio over time on glacier ice cores are sometimes called the isotope paleothermometer. Paleo meaning thermometer of the past. Measurements or inferences into temperature changes based on changes in the hydrogen or oxygen isotope ratios. We know this works because we can measure snow or precipitation falling today at a range of temperatures and seeing how those isotope ratios change as a result. We find more negative delta values in snow and precipitation at colder temperatures. Higher latitudes in the polar regions, higher altitudes on mountaintops, and during the winter, we find snow with fewer heavy isotopes, more light isotopes, producing a smaller heavy to light isotope ratio. This number gets bigger, this number gets smaller. So the overall ratio is smaller, the delta is more negative. The reverse is true when we make isotope measurements on snow falling at warmer temperatures. For example, in the lower latitudes, when we measure precipitation in the tropics, we have more heavy isotope in that precipitation. When we measure precipitation falling at lower altitudes, again, more heavy isotope at warmer temperatures. We get more heavy isotope during the warmer temperatures of summer than we do during the colder temperatures in winter. In other words, at warmer temperatures, we see more heavy isotope in the precipitation. As a result, the ratio of heavy to light isotope gets larger, and the delta becomes less negative as a result. So changes in the isotope ratios measured in glacier ice are a reflection of temperature changes. The way to think about it is it's a reflection of how much cooling occurred along the transport path from moisture source to where the precipitation occurs over the glacier or ice sheet. You can have changes in the temperature at evaporation, changes in how far away the moisture came from, changes in the temperature locally where you're making the precipitation. So changes in isotope ratios are additive of all these effects. So the way to think about it's not a change in temperature at any one site, rather it's a change in the amount of temperature change along our moisture transport path. When there's a greater temperature difference between moisture source and where that moisture ends up, larger temperature difference equals more cooling equals smaller heavy to light ratio and a more negative delta value. Then the reverse is true when there's less of a temperature difference between moisture source and where the moisture ends up. When there's less of a temperature difference, that means we have more heavy isotope reaching the ice core site, a larger heavy to light isotope ratio, and a less negative delta value. So ice cores allow us to measure the concentrations of greenhouse gases in the atmosphere at different times from analysis of the bubbles trapped in that glacier ice of different ages. And ice cores allow us to measure temperature change over time from the ratio of heavy and light oxygen or hydrogen isotopes in the glacier ice itself. In this week's lab, you are working with data from the Vostok ice core. Now, Vostok is in east central Antarctica, near the center of the Antarctic ice sheet. Here, the ice is about 3,000 meters thick. Ice is accumulating at a rate of about 1 to 2 centimeters per year. How long does it take to accumulate 3,000 meters of ice at 1 to 2 centimeters per year? Well, it takes a really long time, on the order of hundreds of thousands of years. As a result, as you drill through the ice sheet in East Antarctica, where accumulation rate is very low, you're getting very old ice. You're able to look at changes in greenhouse gas concentrations in the atmosphere and temperature change over long time periods. The ice core was drilled. This is a look at what the Vostok station looks like. Perhaps one of the most remote places on Earth. This was a station set up by the Soviets, who then made the station available to French, Russian, and American scientists in the 1980s. The ice core was drilled in the mid-1980s and analyzed for greenhouse gas concentrations from the bubbles, temperature changes from the water isotope ratios at laboratories, mostly at French universities. This is what the Vostok ice core data looks like. Changes in the greenhouse gases CO2 and methane from the bubbles, and changes in temperature from the water isotope ratios over hundreds of thousands of years. What you will notice immediately in working with the data is that there's a very strong relationship between temperature and greenhouse gas on these timescales. When temperature is warmer, greenhouse gas concentrations are higher. When temperature is colder, greenhouse gas concentrations are lower. Now, you might be tempted to try to determine a cause and effect relationship here. You might be tempted to try to determine which changes first, CO2, methane, or temperature. Whichever changes first implies a cause and effect relationship with the variables that change later. However, the ice core data doesn't allow you to tell which changes first. The reason for that is there is an age difference between the bubbles, where the greenhouse gas concentrations are being measured, and the ice itself at that same depth. This is because at 1 to 2 centimeters per year, it takes a couple thousand years for snow to be buried to sufficient depths for compaction to occur and seal those bubbles off. In other words, the bubbles are always younger than the ice at the same depth. How much younger is a function of how long it takes for the bubbles to get sealed off, which is a function of the rate at which snow accumulates on the ice sheet surface. We can correct for this by assuming a constant age difference between the bubbles and the ice at a given depth, but we can never know that age difference with absolute certainty. There is some error in the size of the age difference between the bubbles and the ice that contains them, and that error on the age difference is within the timing, relative timing, of the temperature and greenhouse gas concentration changes, which is why you can't tell for certain which changes first. Most scientists have argued that temperature changes first, greenhouse gas concentrations follow, but others have also argued that temperature changes first, and then greenhouse gas concentrations change. The data, however, doesn't allow you to tell the difference. And in reality, it's probably not that important. to tell the difference. Certainly less important than you might think. And the reason for that is a variety of responses where a change in temperature may produce a change in greenhouse gases, or a change in greenhouse gases may produce a change in temperature. Well, it's pretty obvious how a change in greenhouse gases would produce a change in temperature. A concentration in greenhouse gases in the atmosphere slows the rate at which energy is lost from Earth's atmosphere to space. As greenhouse gas concentrations increase, energy is retained in the atmosphere and temperature increases. But how does temperature cause greenhouse gas concentrations to change? Well, it turns out that changes that take place in the ocean in response to a cooling or warming climate change the rate at which CO2 moves between the atmosphere and ocean biomass. There's also a small solubility change. Colder water holds more gases, so when the ocean is colder, it sucks up CO2 out of the atmosphere, reducing the concentration of the greenhouse gas in the atmosphere. When the ocean warms, it holds less CO2. CO2 is released from the ocean to the atmosphere, increasing the concentration of greenhouse gases in the atmosphere. You can illustrate this easily by pouring yourself 2 glasses of soda, leave one at room temperature, keep the other one cold by putting ice in it. See which one stays fizzy. Which one holds more gas? It's going to be the colder one, reflecting the higher solubility of CO2 at colder temperatures. There's also changes in biomass, ocean productivity at different temperatures. It turns out that the ocean is more productive at colder temperatures. There's more phytoplankton activity, more biomass being made, a process that takes CO2 out of the atmosphere, converts it to organic carbon. So when temperature decreases, concentrations of greenhouse gases also decrease. When temperature increases, concentrations of greenhouse gas in the atmosphere also increase. In other words, temperature is both a cause and a response to changes in greenhouse gases. How does the temperature and greenhouse gas concentrations vary as a function of different climates? We have 440,000 years of data here, during which time Earth's climate has changed dramatically between a glacial and an interglacial climate, and changed multiple times. Interglacials are those time periods when temperature is similar to what it is today. Greenhouse gas concentrations in the atmosphere are high, and glaciers and ice sheets worldwide are relatively small. I have highlighted in green the interglacial time periods. Temperature warm, CO2 and methane high, glaciers and ice sheets small. This is what the world looks like during an interglacial climate. It's a world like today. Today we live in an interglacial climate. Temperature warm, greenhouse gases relatively high, and glaciers and ice sheets relatively small. That doesn't mean glaciers and ice sheets are completely gone. It's just that they're not as large as they are during a glacial climate. The opposite is true when Earth is in a glacial climate. This is when temperature is colder than today. Greenhouse gas concentration, CO2 and methane are low, and glaciers and ice sheets are large. I've highlighted the glacial time period. You'll immediately notice that glacial climates tend to last a lot longer than interglacial climates. This is because a cold world with lots of ice is a relatively stable climate condition because of the ability of that ice to reflect sunlight and maintain a colder climate. This is what the world looks like during a glacial climate very different from the one we enjoy today. Glaciers and ice sheets, especially in the northern hemisphere, are large. You can see that much of Canada is covered by a large ice sheet during a glacial climate. The southern edge of that ice sheet at times reached all the way to the Ohio River and flowed out to the ocean at approximately the latitude of New York City. In other words, New York Central Park contains lots of evidence of glacier erosion reflecting the glacial climate, the advance of ice during the colder glacial climate. Long Island, New York, is in fact a large moraine left by the continental ice sheet. Because so much water was locked up in ice during that time, you'll notice sea level is much lower during this time period. For example, Alaska is connected to Siberia during glacial climates because sea level is on the order of 1 to 200 meters lower during a glacial climate, exposing a broad area of continental shelf in this area called the Bering Land Bridge. So again, temperature cold, greenhouse gases low, glaciers and ice sheets large. In other words, why do they call it an ice age? Remember the movie Ice Age? Well, it's because of all the ice. So in addition to investigating how temperature, CO2, and methane change between a glacial and interglacial climate, we can also investigate how strong the relationship is between temperature, CO2, and methane. Previously, we were plotting CO2, temperature, and methane all versus time or age. Well, we can also plot them versus each other. This is called a scatter plot. Two variables plotted against each other. In this case, our variables are carbon dioxide and temperature. We do this to see or quantify just how strong the relationship is between temperature and CO2. If there was a perfect linear relationship, all the data points would plot along that line. You can see there is some scatter to the data points. It's not a perfect one-to-one relationship. There are other factors that affect temperature besides just CO2. But overall, the relationship is pretty strong. A random relationship would have a line with no slope. This line certainly has a slope. It has an equation, again, of the form y equals mx plus b. X is CO2, y is temperature. How strong that linear relationship is shown by a statistic called R squared. R squared is a measurement of how much scatter or deviation there is in the data points from that line. And R squared less than 0.3 is generally considered a weak relationship. And R squared greater than about 0.5 is considered a pretty strong relationship. And an R squared of 1 is a perfect one-to-one relationship between those two variables, with nothing else affecting either one. So in your lab, you're going to make scatter plots of CO2 versus temperature and methane versus temperature to see how strongly those variables are related to each other.